Yeah, thanks for the introduction, Anders. So yes, my name is Nick Wu, and I'm here to talk about transformers, handlers in disguise. And well, I suppose if we're all Haskellers here, then most of us will have heard of transformers and monads and how they relate. And probably quite a lot of us have heard about handlers, because effect handlers have recently become a really important thing for Haskellers. And so you might know that there's this war going on between handlers on the one side and monads on the other side, or monad transformers on the other side. And I even heard at a conference that monads are now dead, and there are no more monads, and the end of the story is there. And so this talk is really about these transformers and whether or not they can somehow unite in some sensible way. And I'll start by talking about effect handlers and exactly what they mean and where we're going with that. And then I'm going to talk a little bit about what I mean by a monad transformers, and I'm going to play some games to try and relate the two together. So what exactly is an effect handler? Well, an effect handler, I like to see it like this. You have syntax on the one side, you have semantics on the other side. And you keep the two separate by this indivisible line, and they don't cross over from one side to the other. On the syntax side, syntax is, roughly speaking, composed of two things. There's the scaffolding in red, and there's the structure in blue. And by the scaffolding, what I mean is, this is the general structure of syntactic trees. There are these things called variables, var, which are the leaves of the trees, and there are these things called constructed nodes, or cons, which are at the nodes of the tree. And you'll notice that the constructed nodes, the cons, are parameterized by the f. The f is the thing that gives the structure to the node. So a node could be something that has a single output, or it could be something that has many outputs, or no outputs, or it could be a node that has some information contained in it. Lots of different options. And those options are provided to us by the structure of the f itself. So in this example, we're using the structure for state, which says that in our nodes of our syntax tree, we either have a get or we have a put. And if you have a get, then it simply continues with some kind of parameter. And if you have a put, it contains some kind of state and then continues with some other kind of parameter. So I'll go through that in a bit more detail in a moment. But roughly speaking, you should think of these as being trees where these parameters here tell you something about how many outgoing nodes there are on this particular node structure.
So state f is an example of the little f?
Yes, so state f is an example of a little f that you would plug into this thing. Yes, that's exactly right. Yes, thank you. On the right-hand side of the board, we have what I would call the semantic domain. And here is where we're going to give a meaning to our trees. We're going to translate our trees from the thing on the left-hand side of the board into things on the right-hand side. And the thing that we're really targeting is this green thing here that we call a carrier. And technically, this is the meaning of the thing that we have inside when we interpret our tree. So this is what we're going to aim for. And to get there, we're going to use this thing called a handler. So these are the effect handlers that people have been talking about. And a handler is some strange thing that takes an alg state, takes a gen state, and I've omitted the definition in this slide. But what you should realize is that alg state and gen state are these two people, and what gen state does, it sort of generates the carrier given an A. And the way to think about that is it's sort of like a var, except it doesn't generate a free FA, it generates something green instead, something in the carrier instead. Similarly, the alg state is a bit like a con, because con takes the f of free FA into a free FA thing, and this sort of takes an f of a carrier to carrier. So it sort of mirrors the con part as well. So there's this relationship between the structure of the tree and the structure of the semantics that's going on, which we'll be making a bit more clear in a moment. So here's more precisely what I mean by syntax. We have here a program, and if you're into effect handlers, this is the future of programming. All our programs are going to look like this, right? Golly. So, okay, what exactly does this thing mean? This thing means, roughly speaking, what's on this diagram down here. It means we're going to get something and then pass on some state s, then we're going to put some variable, then we're going to do some get, and then have some other return value s prime. Yep. Thank you. Yes, so yes, that's me making a typo. These double colons should be gone.
And also the R. I mean,
Yes, indeed. Sorry. Yes. So this is me munging JDT syntax into a slide. So you could replace that with the where here, and then put a statefsk on the right hand here, and then we'd be at the same place. Yes. Sorry, that's my fault. Yep. Thank you. So let's see. The first blob where we're just simply getting some kind of state corresponds to this con getf part. Then the next node corresponds to this con putf part. So remember, these cons are kind of the scaffolding that gives structure to the actual structure inside. So the putf is the thing that gives the structure. And then we have another con getf, which corresponds to this node. And finally, a variable that outputs this, right? But this isn't really the future of programming. I mean, we don't really want to write big, long lines like this. We can at least do some formatting and rearrange the brackets a little bit and maybe just put some new lines and get something that looks like this. This is the future of programming, right? Much better. New lines and spaces makes everything better. Well, OK, so perhaps we're feeling particularly rich, and we can add some dollars to make this thing have fewer brackets on the right-hand side, and maybe this looks a bit better to you. Well, perhaps not. One thing that I do like to do at this point, though, is see here where we have all these different cons and vars. We can abstract away and say, actually, those cons and vars, let's just replace them with little c's and little v's and say that they are kind of abstracted by this con and var here. So all the constructing part has been sort of refactored into one single place, and all the variable creation has also been refactored into one single place. And there's a reason for doing this, right? Because if we just focus on this one expression, if we want to give a meaning to this tree, so this is a syntax tree, what are we going to do? We're going to replace all of the variables with some kind of value in the semantic domain, and we're going to replace all of the cons with something that takes the node that we're dealing with and translates that into the semantic domain. So we want to give a semantics to this code, and what we do is we replace this con and var here with an algebra and a generator instead. So if we sort of go back and forth between these slides, not much changes. What changes is the type of the program. It used to be a free statef int thing, and now it turns into something that's inside our carrier. And what changes down here is we no longer have con and var. We now instead have interpretative functions that will replace all the cons and all the vars inside our program with something that interprets meaning instead. Yep.
This looks like a concrete instance of a type flagless final encoding.
Yes. Yes, that's right. Yeah. So this kind of makes it very clear that we're translating things as we go through this representation. And what a handler is this structure down here. And so this is the definition I'll give to you. And if you're sort of well-versed in these things, you'll notice that this handler is nothing other than just a fold over the structure that we have in this tree, using alg and gen to replace the elements as you go through. So it's a recursive definition that goes right the way through. So the semantics of a program are precisely given by a fold over that program, where you change the meaning of that program as you work your way through. Okay, that's essentially what a handler is. So let's just concentrate on this thing here for just a moment. And how might we improve this piece of code? It still doesn't really look like the future of programming. It still doesn't look very nice. What are we going to do with this thing, right? Well, a couple suggestions. We could probably clean up the syntax. This looks pretty messy. You've got dollars everywhere, and you've got these cons and gets, and it kind of just doesn't look quite right. And, well, we would like to wrap up the semantics so that we really have an object that we're targeting. It's not just this sort of int to int thing. Let's try and be a bit more abstract with that so that we can say, this is what we mean as a semantics. It's an actual value. So enter the monad. This is where monads come in quite handy into this story. So even though effect handlers are thought of a way of competing against monads to a certain degree, at the heart of effect handlers is the free monad. So I won't spend much time explaining this. I hope we understand monads. But suffice to say that the bind operation we typically think of as being something that, given a computation, will say what happens, combines that with another computation and gives you a final result. So it's a way of chaining computations together. You start with something and you extend it with another one, and you carry on through. When we look at the free monad, so this is the free structure that we had earlier on in red. This is the scaffolding, so to speak. This also forms a monad. And this monad has a slightly strange property, because the bind for the free monad doesn't sort of schedule things in the way you might expect it to. What it does is it allows you to graft a computation k onto the end of the tree. So imagine a large syntax tree. Imagine variables at the leaves of this tree. And your k is going to traverse down through the nodes, find a leaf, and replace the leaf with the function applied to that leaf. And that's exactly what we have in this definition. So we're going to say we have an operation, some k, and this part here is going to recursively descend down through the tree and find the place where we eventually hit a leaf, a var, and then we're going to simply replace that leaf with the operation that we have. So this is a way of taking a piece of syntax and adding new syntax to the bottom of that syntax. So this thing, which is what we had before, is a monolithic piece of code. It's monolithic because you can't separate out into separate pieces. It's kind of one big chunk of code that sort of has the continuation inbuilt into it. And instead, we can use the free monad as a monad to kind of plug in different bits of code together. So each of these lines before the bind, you can think of as being a new program that we're grafting on to the old program. So this is a much more compositional way of working. This is nicer. And furthermore, well, we're Haskellers, so we can transform this thing with binds into do notation, and so it looks even better, right? And what we're left with is really these con getfs and con putfs. They're a bit annoying as well. So we can sort of use a where clause, and we can just rename those things and use smart constructors, and then you get a program that looks like this. Okay, so this is the same program as that single line we had earlier on. We've done a bit of manipulation, and now we've got something that's more compositional and that looks better on the eye and is easier to use, right? Okay, but we hadn't really given a meaning to this thing yet. Well, we gave a meaning, which was the one where I gave a handler over the generator and the algebra. But we could also give this some monadic semantics, right? Because who am I kidding? We all know that there are these things called state. There's the state monad, okay? We're all aware of this thing. And if you look, well, the state monad is basically the carrier that I was talking about earlier on. It's the thing that wraps that up. So this is where we're dealing with problem 2. We want to wrap up the semantics in a clean way, in a clean packaged way, and we can do that with this new type constructor. So we're saying the semantics is the result of doing the state S thing. So we know that this happens to be a monad. And actually, something that we tend to do as Haskellers is we tend to generate a specification for the properties that this monad gives us over and above just the monadic bind and return. And that specification is in terms of a class. So we're going to give this class, which we'll call monad state. It has a get operation, it has a put operation, and it has some associated laws, which I won't state. But suffice to say that there are laws that state that deal with how the put and the get interact with each other. And if you don't adhere to those laws, then you don't have an instance of monad state. So down here is the instance that satisfies this, and you can do some calculations and work out that these laws are good. But this is precisely the point that people would object to using monads, is that you have to go and prove these properties, and that's a bit of a pain in the neck. And that's why effect handlers are often shown as being something that's slightly better, because you don't need to prove any laws about how the things interact. They kind of automatically do it by some algebraicity property. Well, let's look into that a bit more. So when we know that we have a monad in our hands, right, which we do because we all know about the state monad, then what's the game that we're playing exactly? We can provide a generator and an algebra for our free tree that we started with. That's the thing that we had at the beginning, right? And the generator and the algebra make you work a bit hard, and you have to do some plumbing to put things in the right place, and there's a bit of thinking involved there, fine. Or you could give a semantics in terms of the state monad. And I argue that here, this definition on the bottom is much clearer to understand than the one on the top. Because if you have a generator, you always return. And if you have some kind of algebra that you want to calculate, well, you just do the monadic action that you expect for that piece of syntax, and you carry on with some k. Okay? So I would claim that even though this thing here might be simpler in some sense to define intuitively, this definition down here makes a lot more sense. It's much clearer in terms of what's going on. But of course, you had to pay for that intuition. You had to pay for that intuition by understanding monads. But we do understand monads. We've done that work. So this definition here, to me, works quite nicely. So now we're on to something that is something that annoys me a little bit about programming with monads, which is to say, well, often we write something like state int, and then eventually we're going to have a whole stack of these things. We're going to use monad transformers to layer on monadic computations onto this thing, and it gets bigger and bigger. And very often people deal with a concrete representation state like this, or they might deal with the free state f int here, and they work with that, right? And I claim that we shouldn't be doing that. We should be programming to an interface instead. We should be programming to something with a signature like this that doesn't say anything about what kind of monad we're dealing with. It just says we have a monad M. It's a monad M that has some kind of monadic state inside of it. And this avoids lots of problems that we get with very large monad stacks of transformers, because if you're programming to the interface of classes and not programming to the specific stack that you're dealing with, then it doesn't matter when you change and extend your stack. You always program to an interface in the first place anyway. So when people use monad transformers and they have these huge long stacks, you want to be careful. Think instead about doing that in terms of a whole bunch of classes that constrain the monad that you have, and then when you actually want to run your monad, that's when you choose which stack you had in mind. So you only need to change your stack one place rather than all over your code. So there's an asterisk here, because I've lied just a little bit, right? I've said that here we have a program. We've got this get and put. We want to unify this into being some kind of monad state thing. And I'm lying because here the get put laws, whatever they be, they're not satisfied when we deal with a free monad. And they're not satisfied because you can distinguish between the piece of syntax that says get and the piece of syntax that just says get. And that's one of the laws that you'd want to have satisfied. So the fact that you can distinguish the syntax means that the laws are fundamentally not holding in the way that you'd expect them to. But modulo the semantics, it should all work out. So now I want to talk about something related, obviously, effect classes. So this is the monad state that we had. And really, we'd like to work with something that's more general than this. Can we abstract away from single class instances like monad state into general things so that we can have more than one kind of effect? And we can encode this signature here as a GADT. And so we can say, well, look, this get corresponds to this get, and the return type is MS, where we've specialized M to be state S. And similarly, put takes this S, and it returns some kind of M into blank. So this JDT, in a sense, captures the syntactic constructs that we have up in this class constructor. And what we really want to do as well is tie that syntax that we've just created with the JDT, tie it to a semantics. What is the meaning of this piece of syntax that we've got? And so here we can introduce a new class, which I'll call monad F, which is the monad that gives an effect to a piece of syntax. So the F function takes our syntax FA, so the F would be something like state SS, and it ties that down to the monadic thing that we had in mind that it should correspond to. So for instance, the F of get is get, and the F of put S is put S. So no surprises here. So what we've just worked on is we've made a way of making more concrete the class structure as data rather than just as functions. Okay? And so how does this relate to handlers? What does this have to do with the talk? Well, let's have an adventure. Effect handlers use a functor, and it's a functor like this, which is the first thing that I introduced. And the type class that we've just had, that we've induced from the monad state type class, is going to make this JDT down here. And these two things have to somehow be related. I mean, there are certainly similarities between the two. Here we have no argument, and here we have no argument, and here we have an S, and here we have an S. You know, here we have an S at the back, and here we have an empty at the back. So there are some similarities between these two things. But there's a big problem, which is that effect handlers require the syntax functor to be a functor, right? That's what makes you able to traverse through the tree. But this thing down here is a JDT, and in general, JDTs are not functorial. So there is no way, actually, to give an FMAP definition for this JDT here. You can't do it. So can we somehow force this to have a functor structure? Well, the answer is yes, we can, right? In fact, we do the left can extension along the identity, otherwise known as the Koyuneda construction. So I don't expect anybody to remember the coordinator construction or even understand what Khan extensions are, but here's the intuition behind what coordinator is doing. So coordinator is a construction that takes our f, and remember the f is a thing that's not functorial, but we want to give it some kind of functor instance. And what we're going to do is we're going to allow the f to gobble up an a, and we're going to carry with us a function from a to r. And that's the secret to how we're going to make this thing functorial, because we're going to, this r is precisely where we can append more and more computations to the end of this thing that we're constructing. So if you look at what fmapf does over our constructed syntax, k, which is this a to r thing, holds the continuation parameter, holds where the rest of the code is going to go. That's where all the syntax that following is going to be. And so the coordinator of our operation is applying our f to the end of this. So think of this as being, you have your tree of syntax, and then at the bottom of your tree, you have this little k that's sitting there inside the coordinator construction. And we traverse the tree with the fmap, and we're going to find that leaf and add the extra continuation on the end of that f. So that's how this works. So the secret is we carry in our pocket the continuations that we wanted to deal with in the first place. So we can recover the same kind of constructors as we had with statef. The thing that the handlers wanted to use was of this type, and we can give it instead the coordinator of get and the coordinator of puts. And if you look at the types, they align exactly. So this is how we can translate from the class for the monadic thing that we had, so the monad state, into something that corresponds to the syntax functor for the handler. So, and so we can give an instance of monad state for the free coordinator state SS, where get equals the con of the coordinator get of var. And var is there because, remember, we need a leaf at the bottom of our tree to graft where the next computation is going to go, where the next piece of code goes. So this is kind of a placeholder for where everything is going to stick onto the bottom. How does this relate to handlers again? Yes. So, well, the handler suddenly becomes really trivial. So if we want to handle one of these trees with a coordinator construction inside it, we can use the fact that our syntax came from the monad class that we had earlier on, that for the monad state, we have that get and the put that we needed. And more than that, we call the get and put that corresponds to the get and put syntax the result of f. So to handle some kind of coordinator free tree, so this is the free coordinator f syntax tree, into some kind of semantic domain MA, what you can do is you can handle, that's to say you fold through the tree, where the algebra is this thing, and at the leaves you simply return a new value. And what is this thing, this algebra cy? Well, it takes your operation that's been wrapped up in a coordinator thing, which holds onto itself this k, which is the continuation where the rest of the code goes. You apply the effects of the operation, as you'd expect, so this does the get or does the put, and then you carry on with k, right? That's all you need to do. So this thing, technically, makes handle cy a monad homomorphism. And that makes people really happy, because that's apparently what an effect handler is, right? And a monad homomorphism basically says that the structure of the incoming monad is somehow preserved in the semantic domain, that we're dealing with a monad-to-monad transformation. OK, so why is this interesting, and why are we bothered with all? Oh, there's a question. Yeah. Yes, so a monad homomorphism is a natural transformation from some monad M to some monad N, indeed. Yeah. So why are we interested in this? Thanks. So composition is really the game that we're playing when we're dealing with effect handlers. And the question is, what do I do when I've got a syntax tree that has more than one kind of syntax in it? So I might have state, and I might have exceptions, or I have state and non-determinism and exceptions. These things can be composed in any order, and I want different kinds of semantics to come out of this. And so it's all about composition, and composition is the thing that people would say allows effect handlers to be maybe more flexible than the monad transformer story. Well, let's have a look at that. So we've shown how handlers relate to ordinary monads, and things get interesting when you think about the composition of effects. And by composition of effects, what I mean is, if you have a syntax functor f and a syntax functor g for two different kinds of syntax, then you can obviously create a tree which contains f or g nodes everywhere in the tree, right? And you do that by saying, well, let's tag it with it's a left node or it's a right node, and you can have either left kind of syntax or right kind of syntax, and so your tree can have more than one kind of node inside it. And ideally, when we want to handle a tree of this kind, we want to do something like this. We start off with the tree which contains all of the effects of f and g. We somehow translate that with a handler into a new tree, which contains just the g. So you want to be able to traverse through the tree, eliminate all of those f's, and turn the semantic domain from an A into some kind of B, which is the residual result that we're looking for. And then you have a tree that's just got G's in it, and you want to go through that tree with a different handler and somehow transform that tree into a final result C. That would be really nice, because then we could just compose two handlers together. We can eliminate all the F's, then we can eliminate all of the G's, and we don't have any tree anymore. We just have the semantics of that tree. That would be cool. But if in practice, this is far too simple for an arbitrary f and g. In fact, it's even too simple for the state example. So the state example looks like this if you try to do this f plus g composition. So let's take a moment to think about that. So here I'm going to do a handle state 2 because I've got two different kinds of syntax. So I've got a free tree which contains state f kind syntax and some arbitrary other syntax g. Don't know what that is, right? And we're going to turn that into, well, whatever the semantics need to be. And it turns out the only semantics that really work is this one here, where the carrier is this s2 free g s comma a. That's already breaking our hope here of recovering just a tree with g's where all the semantics are inside the b, because the state s here has somehow escaped the context of the values inside our tree. So that s is somehow outside already. So we have a problem here. And if we look at the definition, it's going to be very similar to the one we had for the algebra by itself. And the details aren't too interesting, but suffice to say, you have to work for this, right? You have to work out that there's something fishy going on here, and you need to pull something out, and it needs to kind of commute somehow. So something that I'm brushing under the carpet is that there needs to be some kind of distributive law that allows you to pull your syntax through whatever the arbitrary syntax, the semantics are that are coming down the line. And we won't go into the details of that because they're rather technical. But the question I'm asking is, can we simplify this situation, right? And with transformers, we can, okay? And in a sense, it's a really easy statement. But let's see what it means. So we know about state. We even know about the state transformer. We know that it has this structure here. And if you look, this type looks probably quite familiar, because if we look 2 slides ago, or 3 slides ago, this thing said something like s2 free g s comma a, and now we're saying s2 m a comma s. Ooh, that's very similar indeed. M is exactly where we have the free g thing. So, and free g is indeed a monad. So this is a generalization in some sense of the thing that we were looking for when we were looking for a compositional handler. This is the compositional part of that. So this is a monad transformer, which means that you can provide a lift function which lifts the monadic computation MA into TMA. And I like to think of this as being a monad homomorphism as well. This is something that takes the monad M into the monad TM. So it's transforming, as a natural transformation, as we discussed earlier, all of the effects in M into the effects of TM. And if you think about what we're trying to achieve, that's about right. We're starting with the tree, which is monadic, and we're going into another kind of semantics, which is also monadic. So it should be no surprise that transformers are the way there. And so if we look at how we can apply this to our specific case, then we want to be able to say something like, the instance monad M for so given that M is a monad, then if we look at the effects of state S, that's also going to map to a state T type thing, where get is get and put is put. So there's some nice overloading that we can use here that simply says that we can use our get put notation and translate it not into the semantics of a single state, but into the semantics of a state transformer as well. And that will work equally well. So our handle T is going to be the thing that handles our transformed monad, our transformed tree, okay? And so we're going to take our free co-unit of f plus g. So remember, the co-unit of f is the thing that comes from the type class that we started with. And we're going to turn that into some semantics where T, the transformer, is going to transform the meaning of the free G tree. So this T free G tree is kind of like it's a tree inside some kind of monadic context. It's been converted into some meaning, but there's a tree underlying what's going on. The definition is actually quite pleasing in the sense that, so the variables still are the return things. The in L case is the case where we're dealing with syntax that comes from our class. Okay, so here what are we going to do? We're going to apply this fx, so that's going to be interpreting the syntax as the operation that we needed to interpret it with. And then what do? Well, we continue with the continuation k, and we carry on handling the rest of the tree. So we're going to recursively handle the rest of the tree as we go down. And if we have an operation that we don't recognize, that's the thing on the right-hand side, well, we do some sort of joining of some stuff, we do some plumbing, but this is all kind of following from the types, and we put the tree back together again such that we don't touch those nodes, which is roughly speaking what's going on here. So we're going to traverse through the operations and leave them untouched. And you can see that they're sort of untouched because we have a constructor here, and we end up doing an injection here that puts back the constructor that we took out. So we take out a constructor and we put back in a constructor. And there's kind of some mechanics going on there that's not too interesting, but roughly speaking, you don't touch the operation. Is that a question?
Yeah. So could you just remind me what the EFF function was?
The EFF function takes the GADT syntax that says get, and it turns it into the function get from the monad state. So it's going to take your syntax into some semantics. That's all F does. So it's the effect of the syntax. And so we started this talk with this question of compositionality, and the question is, well, can we compose these handlers together? That would be nice to know. Well, let's try to compose two of these together. So suppose we've got two bits of syntax, a co-uninator F piece of syntax and a co-uninator G piece of syntax. That's to say, two bits of syntax that we've recovered from a type class. How are we going to interpret that? Well, we can handle T, the first piece of syntax F, and that's going to leave us with some kind of residual T of a G tree, of a co-uninated G tree. And then we can use HMap to map into the tree that we have that's residual with the handle CY, which handles away that aspect of the syntax. So roughly speaking, we simply just compose two handlers together, and we get out a nice semantics that goes from this strange tree into some transformed monad semantics of the underlying thing. So this is super general because you can do it with an arbitrary two things inside any class that has a monad transformer. And this tells us that we can just play around with our syntax, and what we'll get is a nice semantics that comes out of this thing. And so, what does a stack of size 3 look like? Well, it just looks like this. You start off with your handle T on the right-hand side, which is going to handle away one piece of syntax. Then you HMap handle T, which handles the next layer of syntax that's inside one layer of semantics. And then you HMap handle T, which handles away the thing that's in two layers of semantics in, right? So this is quite nice because you don't have to worry about what's going on. You can just be type directed. And the question is, what's the type of this thing? Yeah? And the answer is, right? Right? So the type of this thing is pretty horrendous. Wow, this is, what is this? Okay, so deep breath. We start off with a free tree, and we've got some F3 and F2 and F1 semantics, and it's sort of terminated with a G. So what does this mean? We've got 3 bits of syntax that we've recovered from some kind of type class, and you have some kind of G that we didn't necessarily. Hint, usually that G will be void. So that simply says, there's no syntax here, there's nothing interesting going on, and you just make it go away. And we're going to take such a tree, and we're going to transform it into something which has this free G thing in, and then hint, that free G tree doesn't really exist because G is going to be void. And we're going to transform the semantics of that tree by T1, translate that by T2, and then translate that again by T3. So we have all of the semantics encoded into this final data type that we're interested in. And what about all this plumbing up here, right? Is it really problematic? Well, what we're saying here is that F1, which is a piece of syntax, has some kind of semantics to do with T1 and free G. F2 has a syntax that has to do with this monstrosity here, and F3 with this even worse monster here. So do we have to come up with these really big monsters where you have to think about how your effects deal with free counit at F2 plus counit at F1, blah, blah. Like, that's crazy. Why would we do that? Well, actually, it's really not that bad. Generally speaking, when we look at our monad M instances, we have parametricity in M. So the M part, the monad part here, we're parametric in it, which means that these parts here, so long as they're monadic, and they are because they're free trees, we don't have to worry about them. So these instances sort of come out for free for us if we're using monad transformers properly. So in conclusion, there's been this great war between monad transformers and effect handlers, and I just think we should get along and help each other to give good semantics to programs. So with that, I'll terminate with Autobots rollout. Thank you.
So you're constructing these trees with a free monad, and a common problem with those is that you bubble through the chain of binds on every new bind and get quadratic performance.
Yes.
So what you showed us, is that the actual implementation, or do you do some tricks like Edward's improve function, or what it's called, in free?
Yeah, thanks very much. That's a really good comment. So the comment you're making, if I've understood correctly, is that when we're constructing these trees, we're constructing with a bind. And the trouble with that bind is that it's terribly inefficient. Every time we graft a new piece of syntax on, we need to traverse through the whole of the tree to the grafted position. So if you start with an empty tree, you go through one piece of syntax, then say you graft one more piece onto that, then you have to traverse 2, then 3, then 4, and so you get this n squared complexity as you go down. Is that the thing you're talking about?
Yes.
Yep. So what you want to be able to do is somehow transform that away, and yes, there are some tricks that you can apply that allow you to do that. And no, that's not in this current implementation I had on the slides, because for simplicity I didn't have that, but certainly you can remove those things through some pretty standard transformations. So not here, but yes, it's possible. And furthermore, I haven't shown here anything to do with efficiency. So you can do cool things like fusion on these trees in much the way you'd expect to. So you can fuse away intermediate parts of the tree, and giving it in this approach allows fusion to occur in quite a natural way.
The underlying assumption here is that those effects are independent. It's like if you have some probability distribution that you might sample from, then.
Yes, the assumption is that the effects are independent, but actually we can slightly play with that assumption. So we've been playing with a sort of simple case where, let's have a look. So maybe we should look at this thing, right? Well, deep in the belly of this beast, the monad F beast, is a sort of type class constraint that says, we're dealing with monad state M, right? And so you might think, okay, we're dealing with individual effects, and they're independent, and they can't interact. Well, there's no reason to have that assumption. You could have a monad M that's constrained both by state and by exceptions, and you have two type class constraints for your abstract M. And who knows what the implementation is, but now it's got two different interacting effects. So you can do that with this technique just as well as you could with the effect handlers technique too.
Any more questions?
So is there a nicer way to write this terrible type?
Is there a nicer way to write this terrible type? Not sure. I imagine you can stick a for all somewhere. Actually, I'm not sure you can write a better type for this, because this is specialized for H mapping these handle T3. So no, I think this is actually the type of this monstrosity. But when you're actually using this monad F, you don't need to provide something that's quite this specific, although you could. So I suppose this is where you can get the kind of thing that answers your question. So your question was, can you have interacting effects? Well, the answer is yes, you can, because you could write a monad F where precisely these effects are interacting with one another, or you could write one that's parametric in the M where there's no interaction between them.
Can you bake in the co-uniter somewhere, maybe into the plus or into the free, so you don't have to explicitly say it every time?
Yes, so your question is, if I've got the co-unator thing and I need to wrap all my syntax, and wouldn't it be nicer to just have that as part of the tree?
Yeah, that's right.
So maybe, but what if you wanted to deal with syntax where you actually already knew where the continuations were for that syntax? So certainly this approach allows you to take a type class and then just run with it and transform that into some kind of semantics, and away you go. And that approach, if that was all you wanted to do, then yes, you might want to abstract away from that process. But if you wanted this to interact also with plain old syntax functors in the old style, then if you keep the tree like this, then you can have both of them interacting. I say that with a pinch of salt because what you don't get when you start doing that is you don't get distributivity for free. So the effect that you've introduced the plain old way has to sort of have a guarantee that it commutes through all the other effects. And that guarantee doesn't come for free. So you have to have some kind of distributive law that's working in there to make that work out. So the handle definition would also have to change for that. So there's a lot going on here that I haven't presented. And it's hard to find that sweet spot where you both allow a transformer form of semantics and you allow a kind of old style semantics with distributive laws. And I haven't found that sweet spot yet.
Thank you.
More questions? I don't see anyone. So, yeah, thank you, Nick.